Hola! Today well, it's the same day, a couple of hours later. Food has been had, which is very nice. We seem to have a replay by YouTube. Let's check the audio. There seems to be a light buzz on the microphone. It's not near any power cables. It is near the case of the computer though, so what if that is a good solution? No, it's not a good solution. Balls. So, this microphone is running on its last legs. I'm gonna have to order a new one. Actually, probably not, because new import taxes are horrendous. But yes, last time we left off, we had a working CPU. It's doing stuff. We could actually go in here, and I'm gonna add a switch up here. And then I'm just gonna bloat every instruction here. So if debug yeah, that's not gonna mess up at all. Actually, we'll just rename the print function to our own function. Just name it PRT, def PRT with a string argument. If debug print argument. So now it's just gonna print output, which is 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45. You get it. But there's a problem, and that is that we are not emulating this correctly. We're having n amount of bits to play with here. Let's just say that Emulators physical computer only has so many bits as well. It has 8 bits. We have n amount of bits, theoretically, with Python. And as you see, we are well over 255, which should be the limit for 255. 255 should be the limit for 8-bit numbers. I'm sorry, that's what I was going to say. See, we're even over 512, so we're even over 9 bits now. Anyway, we have some rectification to do. And to make that rectification easier, I'm gonna create some helper functions, which sadly is gonna have to be, actually no, these can be actually that can stay there because it's a debug function, but my helper functions I wanna put here. Actually, you see, I already have a read RAM, so we have a write RAM. Address value, val value, and you can do a choice here. Either you do preemptive or or the other one, preemptive or... Hold on. Preemptive. Opposite. Why do I have to actually enter the site? Preemptive and reactive. Yes, I guess that works. So either you have... What I'm basically trying to say is that either you do your checks before, well, as your values come into your helper function, or you make sure that everything that goes out of your helper functions are limited correctly. So either you do it at the top or at the bottom. I don't see which one is the better one, but both have their own pros and cons, I guess. So you pick your poison, basically. So right RAM, we're gonna take the RAM, we're gonna put the address equals value. Now that's just how it is. That's just how I do it up here. RAM with the address equals accumulator or value, whatever. Also, that's the thing I did wrong. I assume the A register is accumulator. It's not. So that should theoretically be there. And it needs to be there because of the way flags are going to work in the Turing complete version. So part 3 of this is, or it's going to be part 4 or 5, whoever the fuck knows at this point. Some part of this, we're going to have to come back to this emulator right here and make it Turing complete by adding jump if 0 and jump if carry, yes. And for that we need to separate the accumulator and the A register, even though they could have been seen as the same thing. They're seen as the same thing now because their operation is interlinked. I guess that's how you could say it. They're linked together in a way that makes them the same. After so much as the assembly code is concerned, it doesn't matter. But as soon as this becomes a Turing complete machine, it will matter. And that's just how machines work. If you change how they work, they're gonna change how they work. That's, yes, that's not state obvious. And let's fix this. So let's add our either preemptive or our reactive clamping to this. And in this case, I guess it's both. No, in this case it's preemptive, because everything we write to RAM will be within the range, so everything we read out of RAM will be in the range, theoretically. That's one of the cons, I guess, with preemptive. You could do it the other way around, so you could literally store n value bits in the RAM, and as far as the processor is concerned, it gets a value that's within range, even though RAM actually looks completely different. But yeah, you may run into some kind of emulation problems if you have missed something. That's the thing. Reactive like this masks problems, like nitty-gritty problems, I find. So personally, I would do preemptive, I guess. You find your own style, I don't know. So we have that. Now we have our... I'm gonna group those together even though it looks like shit, and then we're gonna do right. I'm gonna stick with this since the video for... Actually, I couldn't check before, so let's check now. Let's check if... Actually, let's just do this and then do this. What? I mean, that's only for his channel too, to my knowledge. Like, let's try Linus text it. Yes. No. Okay. So it's for all channel pages. If you see them, send this information as text. Screenshots frighten them. Yes. Okay, so let's not dwell on that. The latest video that I... Oh, actually, let's check his website. Oh, God. Does he have the videos here? Well, the latest video I've seen, and with seen I mean that YouTube has like delivered to my front page, because the front page still works, was about conditional jumps. And so the logic exists, but the instruction does not do that yet. So if I could just get a list of instructions, I could theoretically I could implement it without knowing the instructions, but then I have to write my own dummy programs, and that will probably fail because I suck at assembly. And whatever I do, it's probably going to be different from what Beniter implements. So yeah, I'm just gonna keep the A register as the accumulator right now, and this is just gonna live as a comment. So we have write A with value, and we're gonna do A equals. Actually, we don't need. Actually, for RAM we do need a read. But for the accumulator, we don't need a read. Well, a register. It's not technically the same, but it's abstractly the same. That's weird. Theoretically, we're repeating ourselves, so we're gonna we're just going to define a generic bit mask here. That's 255, just as before, but theoretically now this allows us to have an n amount of stuff in our RAM, just as before, so... There we go, 8 of them. Let's have write B. And now we're repeating ourselves, but it's a one-liner, so I mean, if we really don't want to repeat ourselves, we could define a function that sole purpose is to take two arguments and module them together. But why? Is that all? I think that's all. Program counter is restricted to the RAM space, but the RAM address is not restricted to the RAM space, so this right here does that. So since we have two of these here, we're gonna have another bit mask, and now we're gonna have to intelligently name these. So I'm gonna have to name this one high bit mask, and then we'll do low bit mask. Shit. 0B 1 2 3 4. I think that's all. So let's remedy our function set here. So our goal is to replace all of the things in here with function calls. So a equals RAM with argument. Okay, so we're gonna do our write a with a RAM read of arguments. So read RAM with arguments. Easy. Does it still run? Is that a function we use? Do we use LDA? No, I don't think we do. So let's rewrite add. So we set the write B to, wait, what was there? B is RAM. And then we write A with A and B. Okay. Now we are using the add instruction, so let's see if this still, yeah, that's broken as fuck. As you see, we have a bit of an issue here, and that's probably because we didn't define stuff in here as global. Oh, poor me. Global what? B A assignment, good. Reference assignment, good. Reference, good. I think it's now gonna run 3, 6, 9, 12, 15, or whatever. Okay, there you go. It goes. Just by doing that one thing, I think it's actually gonna be wrapping around now. Just because we use the add instruction quite a bit. We add and then out and then jump, so that's basic. Yeah, see, 252, back to 0, and now 3, 6, 9, 12, whatever, yes. Hooray! Why am I... I never thought of that. Modulo and bitwise ANDing is essentially the same thing. When all bits are set to 1. That's a corner case. That's not revolutionary, that's a corner case. You can't really use that, I'm sorry. I thought I had something there. Anyway, it's redundant to modulo it when we can just do this. And actually, let's use that low bit mask that we created. And let's do the same here. And then here we have our separation bit masks. And it should just run. Yes, it runs. Hooray for us. Now there's a 1/10 of a second between each instruction. And there's 3 instructions executed between, including the out, between each out. So yeah, make whatever you want of that. So it should be 1/3 of a second between each of these numbers appearing on screen. And well, okay, before it returned to 0, now return to 2. Wait, that makes sense. Before it got to 252 and then it just went back to 0. Something happened and I fixed it without knowing it. Okay, that's never a good sign. That's unintended behavior that you don't know you fixed. That's bad. That's well, it's a win, but it's a red flag. Maybe it was because I was moduloing it. Let's try and modulo this stuff again. I tell you right now, that's wrong. Why though? Huh. So they're not the same. Okay. Well, this just proves that you learn something new every day. And that you're never done learning. There's always something new to learn. So we have fixed our issue, I guess. Well, it runs. This is a interpreter. And well, yeah, that's about it. It will just sit here and print numbers. Not much else it will do. I mean, we can turn that off and just go balls to the walls. There you go. That's your sequence about 170 times over. And This should be the end of the sequence, and it loops back to 0, yes, 3 seconds, and then back up to 255, back to 2, yes, and it should be 254, and then to 1, yes, and then to, as we saw before, 253, and then 0, and then, yeah. So, also, clarifications. Last stream I touched a bit about on the abstraction level that you make your emulator in. Now this is a high abstraction emulator. It takes the computer as a whole and abstracts it as much as possible. It takes all the available inputs. Well, in my head, well, I would like to think that in my head I took all of the rules for the system and took them to the extreme and see how you can implement that in an abstract way. And as we saw, I, by just sheer luck, assumed that the age register is the same as the accumulator, even though they're technically different registers. So yeah, what I want to get at is this is a high level emulation, HLE. Now, if you want to, you could write this exact same emulator, but what you do is that if we go back to, oh no, I closed it, didn't I? Balls. No. No. Okay, here goes my history. Enjoy this. Where is it? There. No. Go back. Where did it go? There. Dank. Could I? This table right here. If you want to, you could lower the abstraction level to the point that you actually include all of the processor cycles, these 8 processor cycles that are presented to you here, and that you actually have all of the memory, the ALU, as separate objects with separate signals to them, just as the computer. You're essentially recreating it at another level. What I've done is that I've taken what the machine takes and produces, and following the apparent rules that are inherent within the language that you use to represent the instruction set, I've abstracted it to a level that I can just use variables and lists to represent all of these things as, well, in just a glob. And how does one continue this? I don't know. Yeah, it's just a different level of thinking, of how you define stuff. Either you go down in there and you define individual chips if you want to, and you could define individual transistors if you want to. And yeah, you could literally go to any abstraction level you want and recreate the CPU. And what I've done here is probably the most high level thing you could do, which is take the rules of the system and evaluate the scope of each rule and see how far it reaches, and depending on that border and how those borders, theoretical borders, interact with the other rules borders, you can set up your own abstraction, kind of. Anyway, I don't know if you get all of this. So we have one program running. I guess we can't really get access to his other videos since the channel page is literally fucked. Still literally fucked. Okay. Very, very funny YouTube. Jesus. I mean, we could try and write our own quick little program for it here. Let's do that. Let's modify the existing program, this right here, so that it counts downwards. So we're gonna remove this load intermediate right here, and we are gonna replace that. I think it's beneficial if I actually have this out, and if I can see, I should actually label this. I should label all of this, really. So let's do some is that 8? Who the fuck does? 1, 2, 3, 4, okay, that's 8. 1, 2, 1, 2, 1, 2, 1, 2. I think 1, 2, 1, 2, yes. 4, 1, 2, 3, 4, 1, 2, 3, 4, yes. Okay. There we go. So, what we actually have here, let's make it readable. What we have is a 010, actually that I'm reading the wrong way, I'm sorry. Because, yes, when I do say 0 and 1s together, I'm reading this way, like conventionally. But how would I say when I'm reading that way? I don't know. Anyway, we have 1010, which is a load intermediate, and we don't want that. We want a load A. Yes, we want a load A. So actually I'm gonna do this just for more clarification. Which is 1 with zeros. It's gonna get really confusing, like which way I read the binary here. I'm sorry if that gets the case. So we're gonna load the A with the address. Now what's that address gonna be? Who the fuck knows? We're gonna replace that later. After the load A, we have a 0010, I'm sorry, which is a store A, which tries to store it in memory. That's the free we are gonna hold on here. Okay, we're not gonna change this. We're still gonna be have our incrementing or decrementing bar free. So this, we're gonna keep this. We're gonna store that at some location. I think store A at 15. And now we're gonna load intermediate again, and this is the function we want to change to load A. So 0001, just because that's how I typed it. And we're gonna load address 3, 4, 5, 6. We're gonna load address 6. 2 + 4 is 6, yes. I'm sorry, I'm a bit slow in my head. Which means that this right here is gonna be our high byte that we load. So we're gonna load 255 into our accumulator or our A register. It's technically the same when it's not Turing complete right now. And right here. Then we're gonna do 0100. Which is the add from our address, and then we're gonna do our out, and I think that's out, yes. And then we're gonna do 0110, our jump back to here, and we're gonna do that in a loop. But the reason why I added this right here is because load intermediate can only load 4-bit values. Beniter has explained that very well himself. And if you want to load 8 bits into your accumulator, you're going to have to load A. And you're going to have to actually place it somewhere in program space. So that should be address number 6, theoretically. Let's see if this works, I guess. Let's turn on that sleep time again so we can actually see what it's doing. And of course, these should not be here. And we have a failure because we're still adding. However, we did start at 2, which means that our accumulator was, well, A register, had 255, and then it added 3, so it overflowed and went over to 2. Makes sense? Yeah. So we're gonna have to exchange that add function 0100. I'm sorry, I'm just gonna do that again. 0100, I think that's this one. Yes, we add from the topmost address. Instead, we're gonna subtract, which is that. And of course, again, I did the binary thing. Some editors support a way to insert characters in defined numbers and still have them be like read properly and like read properly by the computer and by humans at the same time. It's kind of neat. I don't know why Python doesn't support it, but there you go. Start at 255, we are decrementing. Yeah. Not much about that. Oh, this is why we do testing. Question 1. What the fuck is going on? Question 2. What the fuck is going on? Question 3. Yeah. Is it because we're doing this and Python handles signed stuff a bit weirdly? Is it because in the add thing we're not in the add thing? But what we get in the write A. Oh, we didn't. We haven't updated the rest of our functions. I'm sorry. I'm so sorry. I forgot about all of that. Let's steal this because it's the same. And let's do a. This is why we test. Write A with A minus B. Store A. Store A, which is going to be write RAM. Yes. The argument and A, I think. Ooh. See, that's kind of an oversight, so that's fixed. Load intermediate should be right A. We don't have a right PC yet. Shit. Oh god. Let's try this again. Now it should wrap around as it should, for lack of better words. We are less than 100. If we're lucky, it's gonna go back to 3 digits very soon. There we go, 3 digits again. 253, 250, 247, 244, etc. Works a charm. Now, theoretically, we could change this number here to be that, for example, whatever that is. 167 plus 3. 180. Is that correct? Mate. Did I just fail math entirely? I did. What the f... I said 180, what the f... Why did I get that? I got 100 from somewhere. Lol. So that's correct. Ah, what am I doing? Seriously, what am I doing? Oh yes, I separated the windows. Not much here to tell you. Not much left here to tell you. I should have said, I'm sorry. Yes, we have rectified our wrapping issues. We are pretty sure that the no-op function works. We've tested the load A. We've tested the add, subtract, store A, load I, jump, not null. We have tested out, but not halt. Null and halt both throw exceptions, so they're just gonna work because Python. Things. Not much left here. Ideally, this right here should be put in its different in a function called like step, and this should actually be replaced with a helper function for the program counter. So write PC, PC plus 1. That's how easy it is now when we got the helper functions. We got our data from the RAM, we get the opcode, we get the argument, we increase our program counter, we literally execute the code, which is, we literally execute a function which is indexed from a table from the opcode, and this is the first level of feedback loops that allows the system to not control itself, but it can modify itself according to rules that's defined within itself. So that's, without this, the CPU is nothing. Without this, it won't do anything. Which seems pretty obvious because it just won't run the opcodes, but theoretically, it's still actually ticking through RAM. It's still ticking through RAM, and program counter is still increasing over RAM over and over again. Even though it doesn't do anything, it just increases over and over again. But when you have your instructions which actually execute, you actually have some sort of feedback from the RAM, which allows the processor to then control where you read from RAM again. And Benither got kind of into this in the video I saw about adding Turing machines, Turing completeness to the computer, is that it's kind of like adding a feedback loop. And when I think about it, just having the microcode executing is in of itself a sort of a basic feedback loop. So it's feedback loops upon more complex feedback loops upon more complex feedback loops, I guess. Essentially, as you move up in abstraction, each level has its own, well, probably has its own form of feedback loop. Some may be more complex than others. 10.741 254 251. Okay. Yeah, not much left to see here. There's something I have forgotten to speak about. I'm sure of it. I am very sure of it. Oh yes, last episode, last part, I told you that next full part we'll be doing JITIL emulator. No, that's a misconception. I thought it was gonna be just in time intermediate language because of the Python architecture. But if you bring Python architecture into the mix, then this, what we have here, is technically an intermediate language interpreter, not recompiler, but interpreter. So the intermediate language part is kind of mute because we're coding this in a language. Duh. So next episode is not going to be JITL, it's going to be recompilation. We're going to try and actually not interpret, but we're going to actually try and compile the byte stream that we get, this stream, into actual Python code and all of the crux and crans that goes with that translation. So yeah, that's gonna be real fun, real fun. Sarcasm. But yes, that's all I have to say. I think I did talk about what I just talked about, yes. And I did talk about LLE and high LE. High LE? Low LE, high LE, LLE, HLE. I have a feeling there was something more. Probably not. I can't really think of anything. Hey, that's more legible. Legible. Yes, I can't really figure out what the last thing I was supposed to say, but it was something to do with the recompilation. Oh yes, the jump is probably just like as food for thought until next time. Well, how we'll actually solve this is that how would you implement a jump instruction compiled in Python? Like, think like this. You have your program, like load a equals something blah, b equals blah blah, a equals a plus b, that's our add, I guess, and then our jump. How do we jump back to here? How do we do that? So theoretically there should be minus two. So it's gonna jump to here, if it was to jump. But how do we specify Python to jump in compiled code? That's and furthermore, how do you tell it to skip code? Or something like that. How do you tell it to skip code? And how do you tell it to jump backwards? That's some food for thought that if you're curious, you may try and solve for yourself. Once you kind of realize the procedure that you have to go through and what recompiling actually means, because that's a keyword here. If you want to solve that, you're going to have to look up the definition for recompiling. Just a hint, you take a rule set and you pipeline it directly as a one-to-one copy into another rule set. That's going to be some changes along the way there, but that's a treat for the brain, some food for thought. Until next time, I'm going to hit the stop streaming now and do something else, I guess. Bye bye.